It's a pleasure to welcome today Robert Hargraves. It's always fun to see a Dartmouth alum who has gone on to do so many different things, been a real Renaissance man doing many different activities and doing them well. He has spoken to us before in previous years, and it's a pleasure to have him back. He'll be talking about radiation limits to energy innovation. Just to reintroduce him to you, he graduated from Dartmouth with an AB in math and physics, went on to Brown University to get his PhD in physics, and then, as I understand, was recruited back by President Kemeny to come and be a professor in math and physics here at Dartmouth, and worked part-time developing software for the computer sharing process that Dartmouth pioneered. Incorporated a company while he was here, and really pioneered information technology methods that he later went on to develop at several financial companies that he worked for after leaving Dartmouth. So was a senior consultant at Arthur D. Little, VP and Chief Information Officer at Boston Scientific Corporation, and then wound up retiring from that and coming back to Hanover, and has since taken up a whole new career in nuclear energy technology. In particular, wrote a book called Thorium, Energy Cheaper Than Coal, about molten salt reactors generating energy cheaper than coal. Wrote an article on it in American Scientist, and has been doing what sounds like an international tour looking for prospects to develop this type of energy. So please welcome him. Thank you.
Thank you. This talk comes in two parts. The first part, 10 minutes or so, is a big problem that we have and what we think is a super solution. And the second part, which is most of the talk, is why we can't do it, at least in the United States. Electricity demand is going to increase. These are projections from the United States Energy Information Agency. It's going to increase worldwide by 2040 to by 2,300 gigawatts of average power demand. That's twice the world demand for electricity today. To calibrate your thinking, U.S. demand today is about 500 gigawatts. It's going to double. Where's that energy going to come from? It's going to come from coal. We somehow think coal has been defeated here in the United States by natural gas, but we're going to have 1,600 more gigawatts of coal-produced power. That's going to double coal power electricity production. These are not just speculations. This is a list of coal plant projects and their capacities. All these data can be found. They're backed up. They're in the notes fields of the PowerPoint slides. You can Google this talk and maybe add the name Hargraves and you'll find it. Or if you pick up one of these brochures, there's a website, radiationsafetylimits.info, that has a link to it as well. So, look at the numbers if you don't believe me. Now, understand that coal power has been important to the development of the economies of the OECD nations, such as the United States. And the rest of the world wants to catch up. They want to burn coal. We, who are aware of global warming, say, can we somehow do that without generating more CO2? Let's have the IPCC meetings agree on caps or carbon taxes. And we've had a number of those meetings. There's another one slated to start the last day of this month in Paris. We'll see what happens. A lot of people say renewable energy is the answer. That will solve the problem. Google invested $850 million in their project, Renewable Energy Cheaper Than Coal. And a year ago, the leaders of that project wrote an article in IEEE Spectrum, and I've quoted a few things from it. They say, we need a zero-carbon energy source so cheap the operators of power plants and so on will have the economic rationale for switching away from coal. That's what we want to do with the project ThorCon. What about other nuclear power projects? There's a new plant being built by Westinghouse in Georgia, the AP1000, the latest and greatest Generation 3 plus passive safety nuclear power plant with solid fuel. But if you just do the math with a spreadsheet, just the capital costs amortized over the kilowatt hours that was generated in its life is 7.7 kilowatt hours, cents per kilowatt hour. If you add fuel and so on, we're up to 9 cents. That's not going to be cheaper than coal. Coal power costs about 5 cents a kilowatt hour in the U.S. Natural gas is now underselling it at about 4 cents. So this kind of nuclear power isn't going to solve the global problem. Here's the only physics slide in the presentation. The rows are the atomic weights of some elements, and the columns are the names and atomic numbers. So you see in the middle, there's uranium-235, the fissionable material that is the fuel in almost all of the light water reactor power plants. You also see that blue arrow above it indicating that if uranium-238 absorbs a neutron, it becomes uranium-239 that then decays to become plutonium-239 in the power plant fuel rod, which is also fuel. Perhaps a third or so of the power of a light water reactor solid fuel power plant today comes from the plutonium that was generated from U-238 by that step. In the same way with thorium, we can irradiate it and make uranium-233, which is also a fuel. In fact, that was the driver for the folks at Oak Ridge National Laboratories in the 60s and 70s. They thought about that, and they thought also about a new kind of reactor that didn't use solid fuel at all, but used a liquid fuel. Uranium and thorium dissolved in molten fluoride salts. They designed a reactor that had potentially very low cost, and the technical reasons are basically derived from the fact it's low pressure, not 160 atmospheres of pressure as in today's nuclear power plants. The fuel is fluid, you can just move it around with pumps, and it has an intrinsic safety feature that makes it walk away safe. Our business, ThorCon, is planning to develop that kind of power plant en masse. We seek to develop these in shipyards and manufacture up to 100 1-gigawatt plants per year. In this picture, the yellow hatches on the underground nuclear plant are shown. There's a ship in the background, we call it the can ship. The cans are the reactors themselves and the primary heat exchangers and graphite moderators that need to be changed out every 4 or 8 years. And on the left are just some covers on some ponds that contain cooling water, which is continually circulating by natural circulation that will keep the plant cool in any accident or loss of power scenario. On the right are standard turbine generator halls used by any kind of power plant, such as a coal power plant. We picked those steam generators because we can go out to bid and get the lowest price. They're off-the-shelf items, so to speak. Inside the power plant, let's take a look at the right-hand side first. There's that can module you saw being hoisted out of the ship hold. Inside it is what we call the pot or the reactor vessel. In that vessel are graphite slabs through which molten salt containing the fuel is circulated by the pump. Goes through the primary heat exchanger. At the bottom of it is a drain tank. If everything goes haywire, a little plug of molten salt melts and it all drains into the drain tank and reaction stops. No valves, no controls, no way to stop it. On the left there are examples of those cans in two module units. What we're going to do in a typical power plant is gang two 250 megawatt modules together. One of those cans runs for about 4 years, and then after that, we switch to use the other can and let the first one cool down from the radioactive materials for 4 years, so we can take it out in the can ship back to a refurbishment center, probably just to replace some of the graphite. After 8 years, the fuel is similarly transported to get the fission products out of the molten salt. The innovative idea here is to use shipyard technology. Jack Devaney, our founder, was a guy who built some of the world's largest ships. And Jack's motto is, trust nobody, bid everybody. His strategy is go out, set the specs in place, and get the Korean and Japanese and perhaps other shipyards to bid to do this. If you think about an ultra-large crude carrier, it's tanks and pipes and pumps and heat exchangers and valves, the same sort of thing that is in a fluid fuel nuclear reactor. So his idea is we can use those shipyards, like that one at Hyundai, to do that. A shipyard that size could build 100 of those a year, if you look at the amount of steel tonnage that they actually put together into ships every year. We've done the math. We can produce power, we believe, at nearly half the price of coal power. The capital cost is less, the fuel cost is less. Our objective is to undersell coal plants worldwide so that we don't build all those 1,600 gigawatts of new coal-powered plants. And we can do it quickly. People think it takes 20 years to build a power plant. Just for example, Camp Century was built by a company that never had built a nuclear power plant before, American Locomotive. They designed it, built it, transported it, partly on dog sled, to Greenland, buried it under the ice, got the thing running in 2 years. And those are other examples of quick projects. France decarbonized its nuclear power in about a decade. People also should notice that Sweden did the same. They don't burn coal, nor does Ontario. They use hydro and nuclear power in all those places. So, again, electricity demand is going to increase by 2,300 gigawatts. And our proposed solution is build 100 of these molten salt reactors a year for 23 years. Sounds outrageous? It's a doable project. We can literally stop building new coal plants. Well, we need money to do that, of course. First step is to complete the engineering to go out to bid, about $10 million. Then some money for what we call the phase 1 tests, which are non-nuclear, just basically pressure and temperature testing all the components. Then 3 years of power plant testing with online fissioning reactors, and so on. So that's that. We project the build costs coming out of the raw cost of just manufacturing a product, about $800 million. We project selling them at $2 billion. The market size, 2,300 gigawatts, just to calibrate it roughly, is on the order of $4 trillion. It's an enormous market. So why don't we go out and get some investors to help us? Well, it's not quite that easy. First thing we have to do is, we're going to do it in the U.S., we need a license from the Nuclear Regulatory Commission. That commission was just audited by GAO in July and came up with that number, that is, just the costs of completing the design to the standards required by NRC and negotiating back and forth is going to cost $1 to $2 billion and take a decade or more. So we're not likely to get our investors to say, gee, that's a great idea, because for one thing, the NRC at the end of that period might say no. So that's not a good use of money. So, why? Because people are afraid of radiation. The root cause of the regulatory bureaucracy and time and money is fear. Voter fear, congressman's fear, neighbor's fear, People are unjustifiably afraid of all radiation. Let's see why. First of all, if you Google radiation fear, this is kind of what you get. So we certainly have a problem with sort of the mob mentality, but we also have a problem with some of our best and finest newspapers. This is an article from the New York Times from last year. And you'll see that they claimed that just the CT scans from the year 2007 will cause 14,000 excess deaths. Well, who believes that? Is that right? That's our question. That's part of the problem about fear. People are programmed to write those kinds of articles and believe them when they read them. First of all, we need a few numbers in your head to understand what I'm going to talk about. And that has to do with radiation dose. How much energy is absorbed by body's tissue. In this example, a typical mammogram X-ray, about 2 millisieverts. What's a sievert? Well, it's for basically a joule. If you're an engineer, you know what that is. If you're not, it's a watt second. It's not very much energy, right? A little bit of energy is a joule. So that is a typical X-ray dose. In this talk, we're going to mostly use the word sievert because you see that in the papers. That's the medical term. Sometimes you might see the word gray. They're the same for X-rays, a little bit different for alpha radiation. We told you that the typical mammogram was about 2 millisieverts. Background radiation all over the world varies a little bit. It comes from granite, because granite has in it uranium, which decays to radon and then radium. So there's a little bit of that background. In fact, radon is the largest source of background radiation. It also comes from potassium-40 in food. Potassium-40 is left over from the creation of the solar system. It's mildly radioactive. Cosmic rays from outer space mean that you perhaps increase your radiation by a factor of 10 or 20 when you take an airplane ride because you're not shielded by the atmosphere. So there are some doses, but it varies all over the world depending upon the local geography. But we're afraid of radiation. Look at this picture of this poor girl being more or less frightened to death by these people in white coats who are themselves frightened, of course. What happened at Fukushima? Well, one answer is, well, a lot, but not a problem from radiation. Did not cause any immediate health effects and not likely to cause any in the future. That's the scientific statement about what's happening at Fukushima. But if you look at the death certificates for 1,600 people who were evacuated and moved to let's say refugee sites, their cause of death is listed as stress from the evacuation. So the fear of radiation in Fukushima caused the government to evacuate people, which really did put them at risk. Japan evacuated until just recently all those areas outside that black line. The International Atomic Energy Agency's recommendation would have been to evacuate the area within the red line, roughly. In fact, they have published a document that says what to do in a light water reactor accident. And they say, and this is a picture right out of their document, 25 microsieverts an hour, which is about 220 millisieverts a year, is safe. You don't have to go anywhere for two reasons. One is that the radiation is going to drop off, so you won't get the full 220 for the whole year. Okay? And the other is, it's just not that harmful. And you see we have a baby there and a pregnant woman. That is the IAEA published opinion about what you should do in this accident case. All of this harks back to what's called the linear no threshold theory, LNT. We're going to talk about that for a few minutes. Way back in 1926, Hermann Muller discovered that he could use X-rays to change the genetic makeup of fruit flies. So, depending upon the dosage, he could change the eye color. So, he was the first person to discover that there were genetic effects from X-rays. 19 years later, World War II ended when the atomic bombs were dropped on those two cities. A tragic ending. Everyone was happy the war ended. But a lot of people were concerned that we were entering an age of more atomic warfare. The United States had used both its weapons up in that assault, but they had a production line in Hanford, Washington, making more plutonium in order to build more weapons. The Russian spies had infiltrated the Manhattan Project, and it was almost certain Russia was building the same weapons. So people were concerned that we were going to have all-out nuclear war. So the Nobel Committee awarded the Nobel Prize to Muller, trying to raise public awareness, or maybe fear, of the dangers of atomic radiation. He wrote in the red lines there, in his Nobel acceptance speech, there is no escape from the conclusion there is no threshold dose. All radiation is harmful, which is kind of what he wanted to hear. However, he went on, as an anti-war activist, to try to get a committee together of scientists called the Committee on the Biological Effects of Atomic Radiation. And within a few years, they came out with their report, which said basically there is no minimum. All radiation is potentially harmful. And not only that, it's cumulative. The dose you get tomorrow, today, carries over and is remembered by the body somehow. Don't know how they came to that conclusion, but it is a conclusion you will find that people still wave at us today. These are not true, but we'll come to that. The committee has been reborn several times. The seventh iteration of that committee, now called Biological Effects of Ionizing Radiation, published that chart that I reproduced, trying to explain to the public that, it takes a lot of radiation. It takes 100 millisieverts to 100 people to cause one more cancer. Okay, 42 cancers in a normal lifetime for 100 people. This would add one more. So it's a potential source of harm, according to that 2006 report. But the idea that that the harm is exactly proportional to the dose leads to this kind of idea. That is, first of all, we'll talk about deaths. Roughly, half of cancers will lead to a death, roughly. So 100 millisieverts exposed to 2 persons makes for 1 death. If it's only 1 millisievert, great, except that if we expose 200 persons, we'll get about a 1% chance of death. In the other direction, if we expose 20,000 persons to that 1 millisievert, we get 1 death. If we expose large populations with trivial doses, LNT predicts large numbers of deaths. So the concept of person sieverts, which is just summing up the numbers of absorptions of energy by person, is a quick and dirty way to calculate the number of deaths from radiation exposures. Now, this chart is more recent, but it says that in the United States, the fallout from all the atmospheric nuclear weapons testing over the years ran from, 0.1 to 3 or so millisieverts. So I just wave my hands and say, well, suppose it's about 1 millisievert. That's cumulative over the lifetime of the radioactive materials that fell in the United States. Let's say that for the world. So we had 1 billion people, say 6 billion people in the world. Rule of thumb, we get 300,000 deaths. That's the kind of logic that was being used by the anti-war people to say, well, you may not be afraid of nuclear war, but you ought to be afraid of just the fallout. We're killing 300,000 people. So that campaign led to an effort to stop atmospheric nuclear weapons testing. And it was successful. So there's some good that came out of this. It sort of took the momentum out of everyone getting bigger and bigger arsenals of nuclear weapons with which to destroy each other. We continued to test thereafter underground. But here we are. Notice this all has to do with fear, not weapons. But this also led to another unfortunate idea called ALARA, as low as reasonably achievable. And you get the logic, if any can kill you, we better make sure that all our regulations say ALARA, and they do. Anything you read about power plants or hospital diagnostic procedures will almost always say ALARA, or image gently in the medical world. Reasonable is a vague term, and achievable has to do with the technology. As our technology gets better and better, achievable gets more and more demanding. Here's a typical example. The World Health Organization recommended 0.1 millisievert per year maximum exposure to tritium. But in Canada, where they use heavy water reactors, they create a little tritium. In the U.S., we create a lot less because we use a different kind of nuclear power plant, so-called light water reactor. And so, since it was achievable in the U.S. with light water reactors, we changed the limit to bring it down to 0.4. And that's an example of the ratcheting down of radiation limits that's taken place continually in the last half a century. Back to Fukushima just for a second. If there's a fission product, in this case cesium-137, it decays with a half-life of something like 30 years to a metastable state of barium that then decays to a lower energy state and sends out a 0.6617 signature gamma ray. So if you see a gamma ray like that, at that energy, there's almost only one place it could come from, and that's from cesium-137. And that's almost certainly from Fukushima. So if you're on the West Coast, you might pick up one of these gammas, and you might say, yeah, that's really from cesium from Fukushima. So it's detectable. But some of the most anti-nuclear organizations like Counterbunch say, look, even that amount of radiation, and this is literally the number in their article, is not safe. It's not safe. So that's what's happened to us with ALARA. Anything, any radiation, and that is unsafe, and that makes the public fear anything that has to do with radiation. This man, not far from here in Amherst, Massachusetts, spent his career, or spending it, on dose response. That is, given a dose of drug, what is the human response, what are the relationships? In the last 15 or so years, he's been interested in the dose being radiation, and he's tracked that down pretty well. And he, most recently, published a rather dramatic article. This is the literal article's headline, How the United States National Academy of Sciences Misled the World Community on Cancer Risk Assessment. New findings challenge historical foundations of the linear dose response. I'll break for a second and say these references are all in the notes fields of the PowerPoint presentation. If you want to look them up, you can find those articles and read them. I have a couple of copies here. In a summary, though, he shows from copies of correspondence that before Muller gave his Nobel Prize speech, he knew that LNT wasn't true. But he went ahead with it anyhow because it was important to basically ban the bomb. His colleague Stern covered up the deceptions And eventually, he led the National Academy of Sciences to adopt the LNT theory back in '56. But let's look again at what he said in his speech. Here's the same quotation. I redlined the different words. Doses as low as 400 R. R stands for Roentgen, an earlier dose unit. But in today's dose units, 4,000 millisieverts, that would kill a human. That's a lot of radiation. Remember, 2 millisieverts is a mammogram dose. So the lowest that he experimented with was enough to kill you. And he said, as low as. So he extrapolated his data down to that. That's the basis on which LNT is formed today. They forgot all about adaptive protections. That is, the body repairs its cells as they're damaged and replaces them. So the whole idea of cumulative dose and so on just goes against the grain of any kind of repair mechanism from disease or radiation taking place in the body. Let's look at DNA for a second. It's not a rigid structure. It's fragile. It breaks. It breaks principally from reactive oxygen species, from ionized molecular compounds of oxygen. And it breaks pretty often. A single strand breaks occur about once per cell per second, and they're repaired. Double strand breaks are a little harder to repair, but they still occur relatively frequently. Remember, in DNA, all the molecules are paired, right? So if one is broken, there's one on the other side that tells you what it should have been. There's redundancy in the molecule. A double strand break is a little harder to repair. You lose that redundancy. Just in relevant terms, 10,000 times per day from reactive oxygen species and repairs. If we had 100 millisievert per year dose, we'd add 12 a day. Okay? We're at, what, 3 orders of magnitude less rate from 100 millisievert dose. And similarly for double-strand breaks. The other point is that we know now that there are special enzymes that actually do repair the DNA module, and science has a good look at what these things actually do. And we know it happens relatively quickly. This research at Lawrence National Labs showed that it takes place an order of magnitude of an hour or so. In fact, just last month, the Nobel Prize in Chemistry was given to 3 scientists for their work in analyzing and revealing how DNA is repaired in cells. So this pretty much eliminates what Muller called the hit theory. The hit theory was, if you got hit with some radiation, it might form a cancer that will grow and kill you in 10, 20 years. The hits are repaired. There's another mechanism, and that has to do with immune response. We were talking at intracellular before. The immune response system takes place outside the cellular system. It's at higher level, tissues and organs, and it adapts to strengthen the responses of the cells against assaults of all sorts: exercise, disease, heat, radiation, and so on. Work by Van Endingen and all say that the response is maximized at about 100 millisieverts in a dose. Let's look at some of the fallacies. First of all, let's look at Chernobyl. 28 emergency workers, firemen, who worked on that were killed. They died of acute radiation syndrome. They had way too much radiation. Around the country, the fallout from iodine-131 led to cancers of the thyroid. 15 children died. Many more were treated. The report from the Chernobyl Forum, which is perhaps the most authoritative report, estimates that up to 4,000 additional fatal cancers may happen due to Chernobyl. The word is may, and up to. And I'm also going to point out that that calculation is based on the LNT theory, not having anything to do with adaptive response. But let's look at the death rate from the poor firemen. Okay? It doesn't look like it's linear with dose to me. It's not linear. So there's a contradiction to the idea of LNT. And in fact, somebody did actually count the cancers. Jarolowski was the chairman of the United Nations Scientific Committee on the Effects of Atomic Radiation. What is surprising is that the data collected by show 15 to 30% fewer cancer deaths among the exposed radiation workers. Well, that may be a problem. And the people who are firemen may be more physically fit than the rest of the population. So we have the potential inconsistency of the healthy worker effect in this sample. So then he says, well, look at this other sample. Just looking at the general population, their cancers are reduced. Now, you may or may not believe in the idea of a reduction, but they certainly weren't increased. There certainly is no evidence that cancers were increased by Chernobyl fallout. However, the National Academy of Sciences' most recent report studied with the Radiation Research Foundation over 86,000 people who were exposed to radiation in Nagasaki and Hiroshima. They say, and this is, I'm just quoting their work, the single most important source of data is that. In fact, here is a graph I just copied out of their report. It says, that's it. I mean, you see, I don't see anything particularly interesting at low doses, so what I did was I blew it up, look a little harder, and I don't see anything happening at low doses at all. This is their report. So I'm dumb. I found out that, well, you know, they put all their data online. That was nice. There's the website. I downloaded it into my Excel spreadsheet. And I'm naive, so I just binned it up this way, the way they had it. Numbers of people, numbers of cancers, cancer rates. And then just with Excel, I say, graph it, please. And the little blue dots are what Excel produced. And I drew the red line on it just to show you what a linear response might be. Now, those two cells at 5 to 20 and 20 to 40, to me, look like cancer is going down. It's certainly not going up. Why do they say that there's danger at low radiation doses? One answer might be, well, maybe that's fluky data. Maybe there aren't many people in that category. But, in fact, if you look at the numbers of cases of cancers in the categories, there's a lot of them. In fact, and there's one standard deviation. So they don't look like noise to me. Looks like a real effect. Not only that, that's where most of the people were. 19,000 of them were down in that low dose area. 6,000 in the higher dose. This is the data, and you can go get it. But the reports that come out of the people who did that work mush that data. The low dose region isn't shown at all. They show you only the line generated by the data from the higher doses. These are the data and the reports that are examined by the National Academy of Sciences group to come up with that BEIR 7 report we mentioned. So I think that's wrong to do. Nuclear submarines have nuclear power plants, and they need repairs sometime. They come into dry dock, workers work on them. The steel has cobalt-59 in it. Cobalt is sometimes exposed to neutrons and makes cobalt-60, reactive with a half-life of a few years, circulates through the pipes sometimes, so that there's a low level of radiation that might affect some of the pipe fitters and so on who are working to repair nuclear submarines. So the DOE apparently wanted to know what was the chance of people getting cancer and what would be their liability, so they put together this very fine study. There were more controls than 28,000, but it is a job-matched, age-matched control group. So we can't have a healthy worker effect, for example. And yet, the result of that study was never really published. It was just sort of put on a shelf until these guys back in 2005 found it and discovered that the bottom line of that study said, well, they had a 24% lower death rate, but the 1991 report the DOE mentioned didn't have that conclusion in it. They never looked at the total number or never printed it. So that's sort of puzzling. This is to my mind, a very clear study. There's no healthy worker effect. There's a lot of data in it. How can that be if LNT is true? Now, what the National Academy says, oh, well, that's occupational, and in most cases, first line, the cancer mortality was substantially lower. And then later on in the report it says, but because of the uncertainty, we find that these are not suitable for projection of population-based risks. So they say, this evidence goes against our expected conclusion, we won't consider it. Here is data done by Bernard Cohen, a professor from Pittsburgh, who looked county by county at radon, measured on average, and the death rates for cancer. And if radon was a cause of cancer, and it was a linear relationship, that dotted line would have the dots near it. But to my mind, the dots are pretty well scattered about. I don't see any correlation there at all. In fact, other people have done direct tests of radon versus cancer, and you know what? Radon is not carcinogenic at the levels that are in the environment. So the DOE is telling you to put and the EPA is telling you to put that little radon detector kit in your basement and ventilate it before you can sell your house. Well, you better do it, you won't sell it. But it's not a valid scientific concern. Meanwhile, in Taiwan, they built some apartments. There were steel beams in them. The steel beams came from a factory that used recycled steel. The recycled steel included a cobalt-60 source from a medical treatment machine. So all of the steel was lightly contaminated with cobalt-60. They didn't know it at the time, of course. So we have a nice experiment now. We exposed 7,000 Taiwanese to an average cumulative exposure of 48 millisieverts. They observed 95 cancers. They would have expected 115 normally. But if you believe LNT, then you say, okay, we multiply this way, right? 48 millisieverts over 10,000 to find out that much exposure should have added 35 more cancer deaths, or cancers. So, let's see. We predict 150, we observe 95. What's the chances of that? Well, it's 4.5 standard deviations. Pretty unlikely that LNT is true. Meanwhile, back to the National Academy of Sciences, they say, limited in their usefulness in defining the risk of disease. So again, they find a way to not consider this evidence. Meanwhile, the United States had a program on low-dose radiation effects at places like underground caverns and so on where there wasn't much radiation. And they did some studies, and as these reports were beginning to come out showing, in this case, I've forgotten the biological effect, showing that they were lessened with radiation, funding for the program was stopped. No more funding for low-dose radiation studies. Meanwhile, back in the labs, people did experiments with relatively higher doses for mice, and lung cancer in mice was reduced for those mice exposed to about 150 millisieverts of radiation. Poor beagle dogs were given, during their lifetimes, small amounts of plutonium, which is an alpha emitter, They breathe it, it's in their lungs, and they watched their lung tumor incidences. And there's the result. It doesn't sound like low doses are harmful. It seems like they're helpful. That's strange. What about medical radiation? Well, diagnostic X-rays and CAT scans are really low dose. There's no harm done from them. But therapeutic doses are high. So, for example, if you want to have a prostate irradiated, the radiologists figure out what directions to send the beam and so on to concentrate the dose at the place they want the most exposure. And here's one radiologist's diagram. 78 gray, 78 sieverts. That's a lot of energy, it's a lot of exposure at that prostate. Now, what they do, the radiologists do, is they divide that dose into, let's say, 20 different doses over 3 weeks, so that each dose is smaller. So in that circumstance, the cancerous tissue, which tends to grow faster, is more susceptible to damage. The healthier tissue is allowed to repair during the next day until it's hit again with another dose of radiation. The radiologists know how to do this. They know that tissues recover. But LNT, the theory that is in the law, does not. But there is also a small risk of second cancers from that. These are relatively high doses. Look at 25 gray, for example, on the left there is about 25 sieverts for X-rays. That's 2.5 times, that's 250% of the dose that would cause a cancer, according to LNT. But the risk is small. It's on the order of 1% or so. And if you actually look in the regions around there, we discover that in reality, at the low dose regions, some would say cancers are even suppressed. But they're certainly not harmful in that part of the body where the dose was, say, 10 to 100 millisieverts. Centisieverts in this. So 100 to 1,000 millisieverts. Okay, so now we're going to go through some more data. We won't dwell on it, but the weapons plant in the Soviet Union was sloppy about its environmental control of its radioactive materials. And so studies were done for the people who lived in the area, and it seems that cancer mortality seemed to have gone down, not up. The radium dial painters you've all heard about, remember the people who twirled the brushes on their tongues to get the little numbers and so on? The radium near their mouths caused bone cancers. Many of them died. And yet, the people who ran the plants found out about that, and they changed the procedures so that the women were not so exposed to that much. And so now we have another experimental set of data that shows that actually there was no increase of cancers, in this case, in centigrade for the low doses. The cancers seem to increase somewhere way beyond a sievert. Again, tuberculosis in Canada was treated with X-rays, but there seemed to be no increase in cancers in one report below a certain level. And some people even say there seemed to be an improvement in cancer health at low doses. Total body irradiation is sort of an amazing idea. Let's just irradiate the whole body, not to treat any cancer, but just to stimulate the immune system. And that's been tried a few times. And in this case, had better results than chemotherapy for this particular disease. I know it's also been used for ovarian cancer. So it's a promising area, but of course you couldn't do it in the U.S. So, LNT is wrong. First of all, DNA damage at the cellular level occurs at 1,000 times the rate of background radiation. The concept of adaptive protection isn't included in LNT, and adaptive protections create protection from many stresses. The environmental studies show fewer cancers. We have evidence. The occupational studies show fewer deaths. The atom bomb data, although it was not about low dose rate, it was really a pulse of energy, it did show that there were fewer cancers at the low doses. And we know that radiation exposure experiments to mice, dogs, and people also show low dose radiation suppressed cancer. So, my point is, bad science is the root cause of the resistance to nuclear power. We could solve this global climate, poverty, energy crisis if we only were realistic about what the real risks of radiation were. Here's the bad science. Originally, Muller's deception. Hiding the low-dose data. We've seen that many times in many reports where there is low-dose data available, but they don't put it in the papers. Ignoring the inconvenient truth of occupational and environmental data. And of course, the biggest one is the reluctance to admit errors in the past. That's really hard to do. I mean, these are all scientists who base their careers on the papers they published, and they'll defend them to the death. So that's the problem. And the constant search for harm and not benefit in every one of these science experiments. I'm not the first one to complain about bad science. Here's, in the last year, 2 letters from editors of medical journals that worry about preconceived ideas. All we need to do is invalidate the regulation policy, substitute an evidence-based policy. And I'm suggesting about 100 millisieverts per year. But most importantly, end ALARA, because that's really the source of all the public fear. All we need is science-based regulation to let nuclear power thrive. We don't need subsidies. We can solve the global environmental crisis just with the capitalist system if we can let people build plants that generate energy cheaper than coal. In fact, there's a group trying to change these rules. Scientists for Accurate Radiation Information, for example, has one member who has a nice book, Radiation and Reason. We also have a letter from a researcher in California who has petitioned the NRC to change the limits. We'll see what that brings. I kind of doubt it. But I'd like to see it happen. If you want to go there, the salary website is radiationeffects.org, and you can look at some of the data. Or you can go to my own website on this brochure. There's some in the back, too, that has a link to my own website that has this very presentation in it with all the references. So, electricity demand is going to increase. It's going to double. And it's going to come from coal unless we do something else. The other thing we can do is put in nuclear power plants that generate clean, safe energy. And we can do it with no CO2 emissions if we overcome the radiation limits to energy innovation. Thank you. Okay. That's way at the beginning. These are investors' costs, not just the power plant cost. Oh, I did cover all the slides. That one there? Well, a lot of those costs are complying with NRC regulations that are exceptionally expensive. Not just building the plant, But literally the delays and the paperwork and the lawyer's fees. Remember we said $1 billion just to get the certification.
Well, it costs up to $1 billion to get the certification, but I guess I don't see how $200 million in investments is going to get your plant up and running, and especially not when you're building at a shipyard and you're moving your fuel into a ship and then shipping it to some off-site facility that doesn't exist.
Okay, these numbers came from 3 members of our team who have a lot of experience in pricing ships and other projects. So all I can say is that we believe the numbers. This is the first of a kind plant. Remember, they did. How much is that? $500 million altogether to get the first one up and running.
So, who are you getting your fuel from?
Fuel. Well, we can probably get the 3% enriched fuel easily from the United States or wherever.
No, which vendor? Westinghouse? Is it GE?
No, none of those. No. We'd have to get them from an enrichment company or a downblender. We might get them from the Department of Defense of the U.S. if they want to downblend some uranium. We might get them from Russia. We have a customer who says they can get it. So we can get the fuel.
So then what size is your fuel?
Well, remember, it's liquid. We buy it in a state, perhaps, we're not sure, it's probably, could be either uranium hexafluoride gas, or it could be the oxide, fluoride. We can buy it as uranium fluoride, because that's what we need in the plant, and it turns out that uranium fluoride is an intermediate product in the uranium refining business. So we can actually cut short the fuel fabrication cycle.
So I think it's interesting that you're taking the approach of trying to convince the public that the radiation is acceptable health-wise, instead of just promoting the materials and the features and what you have in your power plant that's going to protect the public. Because every other power plant, that's what they're doing. And it just seems like it would be easier for you to license it wherever, because you're not getting a license in the United States. And if you do get it licensed in Southeast Asia, I doubt it would even be safe unless you actually start thinking about what you need to do to protect the public
Okay.
from all this radiation.
Yeah.
And they're part of the reason why Pilgrim is shutting down, because Pilgrim is, you're right, getting to the point in the NRC where they can't afford figuring out how they're keeping their fuel safe from terrorists who are coming in across the ocean.
Okay, I got to back up and answer the first part of your question first. I would never give this presentation to potential investors. I'm trying to let this audience know why we have such a problem with nuclear power, and it has to do with inordinate fear. You're correct. I would give a presentation talking about the features and benefits and so on of the power plant. This would never come up. And in the countries where we are making this pitch, our expectation is we're not going to have that kind of pushback from the regulatory agency that is so expensive. Because we told them in advance, we don't have the money. It's not possible to do it. It's wasted money. So that's how we answer that.
Yeah,
Yeah, I think
Go ahead.
it's a good question. Replacing sort of one directed conversation.
Do you have a sense that the fear of nuclear power is really caused by the low dose radiation or the risk of high dose radiation?
Any radiation. I don't think the public knows. I mean, we went to a conference over here in Norwich about 2 or 3 years ago where people talked about the radiation at Fukushima, and all the numbers they quoted were off by a factor of 1 million. Nobody in the audience noticed. Doesn't matter. Any radiation is what the public is fearful of.
How much radiation are you predicting your plant makes? You gave us all this graphs, but you're going to put your plant on it.
I no more or less than any others particularly. We basically look at all the specs for the power plants that the U.S. puts together, and we make sure that we meet those. Now, we haven't built the plant.
How much did the other nuclear power plants?
Say again?
Or how much did the other nuclear power plants make?
How much?
You know about your own, like,
Well, the law says something like you can't have more than 0.15 millisieverts exposure to anyone on the fence around the plant. That's what the law says, and I don't think any power plant comes anywhere near that amount of radiation. Okay, so certainly we're within that limit. I can't give you much more than that, except to say the plant is underground.
All the evidence you present sounds pretty convincing. What do the people that you just called, who are doing bad science, say to those? Like, do those people say when they are confronted with that evidence? Have you ever talked to those people that you called bad scientists who did the previous studies?
What do the people who at the NRC say to what? The petition?
To the evidence you just showed us. I mean, when you said that the previous studies that have been done are basically bad science or wrong. Have you ever?
Well, let's see if I hate to show you the slide. We're not going to win yet. This is probably a good example. I'll show it to you anyhow. Okay. Here's what the subcommittee of the NRC on medical uses of isotopes says. He says, should exercise prudence, though not excessive conservatism, in formulating radiation protection standards. Okay, continue to obey formulation based on the NI. These are 4 men, or 4 people, I don't know if men, on that subcommittee who make this declaration. Now, what I showed you was a lot of plots with data on them. The regulatory world deals in these kind of paragraphs. So I don't know what's going to happen. We're still petitioning. Here's an example. The NRC counsel, who just retired, went out of his way to write a letter, and you can look that one up too. He says, hormesis is pseudo-scientific claptrap. Won the support of such notable thinkers as Lyndon LaRouche. This is too goofy for words. So, again, this is the battle that takes place in regulatory circles.
Is there a question?
Last time you came and talked here, you made a major point of the advantages of the thorium cycle in making it more difficult for the proliferation of nuclear weapons. But you haven't mentioned that today.
I haven't. The proliferation is a complicated issue. This power plant is liquid fuel. It's a little different. In a sense, it's easier because we have the fuel in a liquid form already. So if someone were to somehow take over the power plant, shut it down, and send in a bunch of scientists, they have a step up in the path of trying to convert it into a weapons manufacturing plant. On the other side of the coin, there's a lot more radiation harmful from the so-called, from the U-232 isotope that is created in this kind of plant. So it kind of balances out. In retrospect, I think we have to be careful about weapons proliferation in any case. We want to make sure that all these plants are guarded, and we're confident so far that we've got a design that is at least as protective as all the power plants we have today.
Last question.
It seems to be that much of the opposition is what you do with nuclear waste. So what's the issue with nuclear waste with your...
We make a little less nuclear waste, but it doesn't matter to the opponents. I mean, there's going to be waste. We can get rid of a lot of it. A lot of the actinides can be recycled in this plant and burned up. That lowers the heat load on the long-term storage in a geological repository. But here again, there's a few concrete casks outside of Vermont Yankee. They're going to be there for another decade or two. How much of a problem is that? I mean, you can go up and touch the cask. There is going to be waste, and people who oppose power plants will oppose it whether it's 100 tons of waste or 10 tons of waste. It doesn't matter. There's going to be some. We have to hold it cautiously.
I should just make a point, like, the alternative is coal, and coal processing produces a lot of waste as well, and coal slurry ponds and kills lots of people.
Right.
So,
Yeah.
You should compare waste to waste, and when you're having that discussion of the nuclear waste,
Right.
remember that the coal is not a free ride.
Okay. I think we'll finish there. I want to thank you very much for this important topic and debate. I got one of those radon kits. I measured my own basement. It's 10 times the above ground level. So now I can tell my wife when I go down and watch TV, I'm lengthening my life.